This is Mrs. O'Neill for AP Chemistry, Chapter 9, Section 5, Hybrid Orbitals. In this section, you're going to account for molecular shape and consider how orbitals of one atom mix with another, or they hybridize, or they create a hybrid orbital. So pause the video, read as you write, fill in those blanks, and then play to hear my words. So hybridization is just the blend of orbitals. Of course, those blend of orbitals comes from those valence electrons. So just think of anything else. It's a hybrid. So if it's a hybrid, that means the shape has changed a little bit. So this way, you already learned about the s orbital, right, being a sphere. Well, when a sphere from one atom combines and mixes with a p from another atom, well, now we have what's called the sp hybridization or hybrid. So that's why even the labeling is going to be different, because now you have two atoms coming together and now they're mixing. To give you some kind of an analogy, we have here an S, right, because it's a sphere, and we have a P orbital because that's a dumbbell. Well, if we think about colors, we think about yellow and blue. Well, when we mix, when we form that hybridization, when those two atoms come together to mix, to blend, to hybridize between the S and the P, now what color does that yellow and blue make? Green. And look at the orbital. Looks a lot different than how it started. So we have a circle, we have a dumbbell, and now we have this, I don't know, teardrop with a little shoot coming out of it. I don't know what you want to call it. But now we went from S and a P to an SP hybridization. So why does this even happen? Well, let's look at carbon's electron configuration. Atomic number 6, it has 6 electrons, so that's our electron configuration. That should be easy, right? However, we're only going to be focusing on the valence electron, so we're not even worried about the 1s2. We're really only worried about the second energy level. Well, that second energy level has electrons in the s and electrons in the p. Well, how do they look in the orbital filling diagram? Well, we have 2 electrons in the s, because we were all taught that those get filled up before we even start the p's, right? And also in the p orbitals, 1 goes in each one before, again, we start doubling up. Well, this guy's in red for a reason, and look at where those orbitals are. We have an s, and then the p are higher up because they have more energy. Very important. So, what does carbon need to bond? Well, it needs 4 unpaired electrons so it can bond 4 times, because we know that carbon can bond 4 times. But the way this looks right now, we can have an electron here and an electron here, which would only make for 2 bonds. So what the heck has to happen? Well, the Lewis dot diagram for carbon really should look like this. It should have 2 together, right, as a pair, because that would be the 2s orbital, and then 2 singles. However, we know that that's not the case. We know that carbon can bond 4 times. So something has to move over. What moves over? Well, this 1 electron is going to move over here, here, in order to have those 4 single electrons to make four single bonds, right? So what happens is this 1 electron from the 2s orbital is going to jump up. So it's going to go from the 2s energy to the 2p energy, and now look at this. We have 4 empty spots. We have 4 empty spots for 4 single electrons to make 4 single bonds. And we know that that happens. Now the problem is when that happens, that energy now from here to here actually goes into 1. They now all have equal amounts of energy. So when we dealt with the energy, the bond energy, right, the amount of energy needed to break a bond, when we dealt with something like CH4, each of those CH bonds would really have the same amount of energy that it would break. So when they would break a CH4 compound, they wouldn't know which CH bond broke first, and it didn't matter because, again, they all had the same amount of energy. Every time they broke that first CH bond, it would have the same amount of energy. So that's why things hybridize. So we have the 2 and the s, and they come together to make an sp orbital. Okay, so when carbon hybridizes as 4 single bonds, we're going to say SPPP around the carbon, and we're going to have SP3 is going to be what's called our hybridization. And again, here's our energy diagram down here, or the orbital diagram, to understand how that changes in energy. So now these practice problems. It's up to you how you want to do them. I believe there's 8 of them. So if you want to listen to me for the first 2 and kind of plug and chug as you go along, or pause, or you can just play them through and then fill in the blanks, or you can try them all and then check your answers. So it's up to you how you want to do it, but I strongly suggest at least listening to maybe the first 1 or 2, making sure you're filling out the chart correctly, and then maybe pausing the video, and as I click through the last few, I'll just be clicking through the answers. Now again, reminder, if you have questions along the way, put a question mark or a star, and then you can either ask me or someone else in class. So the first thing is first, obviously draw the structure. CH4 should be very easy now. You shouldn't even have to count those electrons. So the shortcut to label the hybridization is labeling each electron domain. Now I want to remind you that an electron domain can be a pair of electrons, could be a single bond, could be a double bond, could be a triple bond, right? Anywhere there's electrons in an area. So in this case we have 1, 2, 3, 4 electron domains, and I'm going to start labeling them S, P, P, P. Now, if there was another electron domain, we would go to the Ds. We would go to the Ds 10 times, right? Because we have 10 spots where those D orbitals can be. If for whatever reason we'd have to go to the F, we could have up to 14 F electron domains. So just something to think about. They don't usually occur, but you never know, they're out there. So our hybridization is sp3. So again, just another picture of it, just to give you that visual and that 3D model. So now let's answer these questions. Again, most of this should be simple. Geometry is based off of electron domains. There's 4 of them, so that's tetrahedral. The shape is out of those tetrahedral, out of the 4 electron domains, how many are bonds and how many are pairs of electrons. Well, here there's all 4 bonds, so that's also tetrahedral. Bond energy then would be, bond angle would be 109.5. Hybridization we already talked about. And if we look at the polarity, all of these guys are H's, so guess what? It's going to be non-polar because the pool is the same for all 4 electron domains. So think about hydrogen. Hydrogen really doesn't hybridize because it only has 1 electron in that s orbital. So hybridization really is based off of an element that's centralized, something in the center, okay, or something in the middle. So hydrogen can never be in the middle, right? Hydrogen always has to be on the outside. So they'll never ask you for the hybridization around hydrogen. So draw the structure. Again, Be is an exception because it only has 2 valence electrons. Hopefully you got something like that. So now let's look at the hybridization just real quick. Again, your orbitals are here. Remember that the 2p, even though there's no electrons in there, because beryllium has 2 energy levels, that second energy level, those 2p orbitals kind of exist there, even though it's not always used. But when beryllium does join with another atom, it's now going to hybridize in order to make those 2 bonds that we know that it can. So it goes from an S and a P to sp hybridization. So again, we're going to label here each electron domain sp, so we get sp as our hybridization. Now, this is just a nice picture of, again, how those hybridizations, how those S and Ps are actually coming together. Now, can you answer these questions? Hopefully you can. Again, geometry is based on electron domain, so it's linear. Shape is how many bonds versus how many lone pairs of electrons. Again, 2 bonds, linear. Bond angle, you saw before, 180. Hybridization, sp. And we have 2 H's. Those are the same, so it's going to be non-polar. So again, just another picture of how the atoms blend together, or how these S's and P's blend together. So can you draw NH3? Again, that should be another quick one, and I'm going to start clicking through this one. So at this point, you might want to pause and try to fill in as much as you can, and then click through the answers. Now the geometry is tetrahedral because there's 4 electron domains. However, there's not 4 bonds. Now we have a single pair of electrons. So the shape now is a little different. It's going to be triangular, pyramidal. And of course now this one's polar because those pairs of electrons are going to be a quite different pool than the regular hydrogen atoms. Okay, clicking through. Again, just to show you that energy diagram and how that works. Hopefully that makes sense, and again, if it doesn't, please ask in class. This one has a double bond, so now there's 2 carbons. So now we really have hybridization around this C, and we have hybridization around this C. So another thing to think about also is that this one double bond area counts as one electron domain. So we want to make sure of that, right? So it has a one large bonding pair, okay, or electron domain. So now in class and on your tests and on the AP exam, they might say to you, what's the hybridization around the first C, or the terminal C, or the middle C? In this case, there's no really middle C. Now in this case, the 2 C's are the same, so it doesn't matter which C we're talking about. But if you do have a long, rather big organic molecule, they might actually point out which C they're talking about. So again, each C is sp2 in this case. So what's the geometry around C? Again, they're going to be the same in this case because they're both the same. And hopefully that makes sense. Just a nice picture again to show you how things are hybridizing. Now we have a triple bond. I specifically made sure to have, again, single, double, and triple bond so you see the difference. And remember that those areas are still considered just one electron domain, or one large bonding pair. And again, both C's are the same, which is nice. Now can we do these questions? I just wanted to show you the different hybridization of carbon again because you'll see a lot of organic compounds. So when it has 4 bonds versus 3 electron domains versus 2 electron domains. And again, just to show you some pictures of how those S and P's are coming together. I know some of you are real visual learners, so hopefully this will help remember things. Here's your sp2 hybridization, what that would look like. And sp2 again, just to give you an idea of what's going on too with the energies. And sp3. Looks kind of funky, huh? So can you do number 7? Uh-oh. 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 What would be next, right? So you have one S, you've got 3 P's, and what's the next in the electron configuration? D's. You got it. So this hybridization is going to be sp3d2. So again, what's the geometry? And of course it's nonpolar because they're all fluorine atoms. If one of these, even just one, would be a different element, then it would be polar because the pool or that electronegativity would be different. And I believe this is the last one. And it doesn't really matter the order of the electron domains. I kind of start here and go around. If you want to start here and go around, if you want to start at the lone pair and go around, it really doesn't matter as long as you hit every electron domain. I just like to start somewhere and go kind of clockwise. So can we answer these questions? Again, it's octahedral, but now you have that one pair of electrons there, that lone pair, so it changes the shape to square pyramidal. And hopefully that makes sense. Again, with that lone pair, it's now polar. So you should be able to do this. So pause and make sure you're understanding and you can do all of this. And sometimes they word it this way. So those are all things you should be aware of. So this is the other thing to think about. So the hybridization depends on the electron domains. So this is why the worksheet that you have, linear would be sp, or I should say 2 electron domains would be sp, and the 3 electron domains would be sp2. Whether it's triangular, planar, or bent, it doesn't matter. If it has 3 electron domains, it's going to be sp2 no matter what. Same thing with 4, 5, and 6 electron domains. This is, I just thought, a cool looking picture as to what hybridization is and what those atomic orbitals look like. So again, if you want to pause it and have a little bit of reading, that's great, but I just thought that was neat. And I also found one in black and white, so I thought that was pretty cool as well. Okay, we will see you in class. Hopefully most of that makes sense, and it's pretty easy. We're just going to go with that shortcut.